Hey kids, it's Mr. Martin, and today we're going to talk about Chapter 4, which is the atmospheric energy and global temperatures. When we look at energy that comes from the sun, part of it comes in and goes all the way to the surface and absorbed there, which is about 45% of the energy from the sun. 24% never makes it because it's absorbed in the atmosphere, and 31% is redirected back out into space. Now, this energy from the sun comes in as shortwave radiation. And that shortwave radiation either bounces off or comes to the surface. But once it hits the surface, it leaves as long-wave radiation. The wavelengths actually lengthen out. So it comes in shortwave, leaves long-wave. So when we talk about temperature, there's three temperature scales. The first one is Fahrenheit, which most of us know because it's the scale that we use here in America. And that is where ice melts at 32 degrees Fahrenheit, and the boiling point is 212 degrees Fahrenheit. So if you boiled water on your stove, when it's boiling, it's actually at 212. Now Celsius, on the other hand, that is the metric unit of temperature, and it's adjusted to a 0 to 100 point scale, where 0 point Celsius is ice melting, and 100 degrees Celsius is ice boiling. And for extremely cold temperatures, you have the scientific Kelvin scale that measures down to absolute zero. And absolute zero is at negative 273 degrees Celsius. Absolute zero is the point at which atomic and molecular motion in matter completely stops. So you wouldn't want to be at absolute zero. So let's talk a little bit about Earth's hottest temperatures ever recorded. Over here in Iran, it was 159.3 degrees Fahrenheit. In China, it reached 152.2 degrees Fahrenheit, and over here in Queensland in the desert, it reached 156 degrees Fahrenheit, which are very hot temperatures. When you look across the equatorial belt, most of your hot areas are those areas that are close to the equator. The further north you go from the equator, the colder it gets, or the further south you go from the equator, the colder it gets. And that's because latitude is the primary cause of differences in temperatures. So at low latitudes, like Salvador, Brazil, you have very constant climate and stays warm all year long. As you go further north to like New Orleans, Louisiana, it's cold in the winter, warm in the summer, but still pretty moderate in the winter. Montreal, Quebec, which is at 45 degrees latitude, is very cold in the winter, warm in the summer, and very cold as it goes back into the next winter. If you go all the way up to 71 degrees north latitude in Burrow, Alaska, it's all very cold. It gets all the way to a balmy 40 degrees Fahrenheit in the height of the summer and then goes back cold. So they're always cold up there. And the main cause of that is because they're at a very high latitude. Another thing that impacts temperature is altitude. The higher you go up a mountain, the colder it gets. So that's because at the top of the mountain, the air is less dense, and so it doesn't hold on to the heat as it does at a lower altitude. Another thing that impacts temperature is cloud covers. If there's a lot of clouds in the area, it tends to keep the temperature much more stable, meaning that it won't get as hot as it would on a sunny day, and it wouldn't get as cold as it would in the winter if you have a cloud cover. It insulates the earth. So there is a difference of the sunlight coming in and insolation or solar radiation that hits the land and warms the land versus that hits the water and warms the water. The water absorbs quite a bit more of the heat from the sun, which causes the water to actually have different temperatures across the globe. Just as the earth has different temperatures, sea surface temperatures are different. Just as you'd expect, warmer along the equatorial belt, colder the further north you go. So what you end up with are all these currents throughout the ocean that are predictable because of the uneven temperatures from the sunlight. So the effects of this is the term marine effect describes the lower temperature ranges of locations by the ocean. For example, if you look at San Francisco, California, that is on the Pacific Ocean, its temperatures throughout the year go up and down, but not significantly like a place like Wichita, Kansas, that's a very continental climate in the middle of the country, where you don't have that ocean acting as a grounding effect or a leveling effect of your temperature. So it's much colder in the winter and much hotter in the summer. Now, if we look at the temperatures globally at the different times of the year, this is the January temperatures, and you'll see that most of the United States is cold in January because it's our winter. Remember, that's where the tilt is towards the sun for the southern hemisphere and away from the sun from the northern hemisphere. If you go to July temperatures, the tilt is opposite because the Earth is on the opposite side of the sun. The tilt doesn't change. It's always 23 degrees the same direction, but because the Earth is on the opposite side of the sun, we are now further from the sun, which is why in July you've got much warmer temperatures in North America and the northern hemisphere, and the southern hemisphere is in their winter. So global annual temperature ranges, this map's kind of neat because you can see these continental areas over most of Eurasia and over North America. Those are those areas that have those continental differences where they're not protected by the leveling of temperatures by the oceans. So when you look up here, you can see this continental ridge all the way across this landmass where the temperature ranges go up and down much further, which is why, like we said, San Francisco out here on the ocean doesn't have as large of a swing in annual temperatures as Wichita, Kansas, that's impacted by this continental phenomenon. Okay, let's talk about polar temperatures. You can see in this model in January, this is when it's hottest at the South Pole because in January, the South Pole will be pointed towards the sun from the tilt. And you can see it's negative 30 degrees here on this temperature map. And then in July, when it's winter in the southern hemisphere, it's much, much colder in Antarctica. So that's another impact of the tilt as the Earth rotates around the sun. We also, as people, can impact the energy balance, and that global temperature increase is happening, and we can also talk about temperature increases in urban environments. Globally, since 1880, when the instrumental climate record began, Earth's average surface temperatures warmed about 1.4 degrees Fahrenheit. And since 1970, global temperatures have increased an average of 0.3 degrees Fahrenheit per decade. So we know that we are in an upswing in global temperatures since the 1880s. What's argued when you talk about global warming is that an impact of what we as humans are doing, or is that an impact of the climate naturally fluctuates over time? Well, the interesting phenomenon when we look at this is one of the things that is also true is that we are having an increase in atmospheric carbon dioxide, which are pollutants from emissions of carbon-based engines. And so when we see this carbon dioxide increasing significantly, at the same time you're seeing a temperature increase, most scientists believe that these things are linked, which is that idea that the globe is warming. Another issue about how people impact temperature is urban heat island. And basically, if you are in the middle of a city, like the middle of Dallas, if you watch the news some night, you'll see Dallas will be a few degrees warmer than out here in Irving or way out here in just north of Denton or Decatur type area. And the reason is that the more concrete that you have and the more structures that you have, it actually absorbs and keeps heat. So you can actually look at a heat island effect in any large metropolitan area.